Hello, everyone. How are you today? Thanks for joining us for this webinar. Today, we will be talking about final elements. We're going to be talking all about the final elements. For those of you that do not know me yet, my name is Loren Stewart. I'm a CFSE here at Exida. For those of you who do know me, you might know that I sound a little different than normal. So please excuse my voice if it does seem to crack at all throughout this presentation. I mostly work with our mechanical customers along with doing a lot of our trainings and courses. In case you are new to who Exida is, I'd like to say no matter where you are or where your customers are, we have somebody close by to help you with any of your functional safety needs. So whether that's functional safety itself or process safety, alarm management, or cybersecurity, we have the experts, the tools, everything to really help you along the way. And we're not just involved in like one or two of the little segments in functional safety. We're involved in the complete supply chain of functional safety in multiple different industry sectors. So whether you're the OEM who require product certification through to the end users that use that product, Exida has software tools, we have training, we have consultants. We can have our people help you to make your functional safety, security, and reliability needs just go so much smoother. I mentioned briefly our engineering and consulting services, but yeah, we have those. We have consulting in process safety or functional safety, which you might be familiar with if you're attending this webinar. But we also have consulting in alarm management and or cybersecurity as well. I also briefly mentioned our tools, and we're going to get a little snapshot of one of the tools that we have today. But our tools were really designed to encompass all of your functional safety needs. And when doing that, we try to help save you time and money. Well, how do we do that? We're going to increase your efficiency and your productivity. So if you're trying to do PHAs, LOPAs, SIL verification, SIL selection, or even cyber risk assessment or alarm rationalization, we have engineering tools that can make that process go smoother for you. And then the last plug on Exida before we get started into why you're really here, Exida certification. So if you're an OEM, you might be getting your product certified. If you're an end user, you might be using those certified products. But Exida has product certification in IEC 61508, 511, tool qualifications, ISA secure, cyber risk assessments, or cyber certification, excuse me, machine certification, and personnel certification. So today, let's learn about final elements. We're going to look at what a final element is, what's all included in them, key equipment selection criteria. We're going to look at what is important for your SIF and end up with failure rates. Throughout this presentation, if you have any questions, please feel free to put them in the questions bar. I try and take a little time and see if questions come in throughout it, but I'm really bad at doing that. I'm not going to lie, so I always save time at the end to answer all of your questions though. For those of you that might be new, we record these webinars. So if you want to listen to this again, we'll have it on our YouTube channel or Exida website. And for anyone who signed up for this live webinar, you'll receive a copy of this slides later this week or early next week to your email. But let's get started. This might sound elementary, but I like to start at the very, very basics. What is a final element? We all might have different idea of what a final element is in our head. So I just want to make sure we all have the same definition to build this webinar upon. So final elements can be many, many different types of devices. The final elements that we're going to be concentrating on are devices that can be used in safety systems. And these can include annunciation devices such as horns or flashing lights or sirens in any sort of functions that are designed to alert somebody to have a consequence reduction. So somebody is alerted, or the sirens are going off, the horns are going off, you're going to reduce the consequences of an accident. Some safety instrumented functions, or SIFs, which I'm going to be calling them throughout the presentation, can be simple, actually only comprising of one device. You might have a relay or a motor contactor or a solenoid valve, and you can use that, just that alone, as your final element. Or you could have a more complex SIF. You could have a machine control application where a final element may be your motor controller, or a device such as complex as a clutch, or a brake assembly, which requires removing of kinetic energy for your SIF. So as you can tell, when I first thought about functional safety and final elements, I was just thinking of the valve alone, that last piece. But final elements encompass so much more than that. So to begin, we are talking about a SIF, and this is an example of one of the most simplistic SIFs, not the most, but one of the most simplistic SIFs you can get. A solenoid with an actuator and a valve. You put them together and you can control and open that valve or close that valve. In the process industry, the most common final element is actually a remote actuated valve. And this assembly usually consists of a pneumatic or a hydraulic control assembly, an actuator, and a valve. And that control assembly may be relatively simple, such as just this, 3-2 solenoid, or it could be more complex, such as a smart partial valve stroke device, or a complex electro-pneumatic assembly with solenoids, test switches, pneumatic booster relays, flow regulators, vent protectors, and quick exhaust valves. So as you can see, our example of a SIF, just our solenoid actuator valve, is relatively simple, but let's take that idea and build upon it in this webinar. The different devices that can go into the SIF, once again, depending on how complex you are, depends on how many devices you're going to have. But we're going to look at 4 main device categories, and I'm going to start off with your final element interface devices. 3 of the main categories are a solenoid valve, a quick exhaust valve, or a volume booster. But there are other things like filters, flow controls, restrictors, silencers, regulators. All of those are also included in your final element interface device category. Probably the most frequently employed device for controlling safety valves is a solenoid. Solenoid valves are available with various porting configurations. You can have a very simple poppet design, a 3-way solenoid to a 5-way and beyond. So Even solenoid valves themselves vary on complexity. A solenoid valve, in the simplest implementation of it, utilizes a change in an electrical signal to control the flow of the fluid or your process flow. Solenoid valves contain a coil which generates a magnetic field when it's energized, and that field acts on a magnetic core piece which is inside the solenoid, causing it to move. It can either be causing an opening or a closing. In a direct acting configuration, the movement of the core will either completely open the fluid flow or close it. The next category of devices that can be considered a final element are motor controllers or starters. A motor controller is a device or a group of devices that serves to govern some predetermined manner the performance of an electric motor. A motor controller might include a manual or an automatic means for starting and stopping that motor. Selecting forward or reverse rotation, selecting regulate and making sure the speed is regulated, regulating or limiting torque, also protecting against any faults or any overloads. There are three main types of starters. You have your direct online, your star delta starter, and your auto transformer starter. Many motor controllers can manually, remotely, or automatically be operated. They may include some means for starting or stopping the motor that may include other functions or just that function alone. An electric motor controller can be classified by the type of motor itself that it drives, such as you might have your alternating current or your permanent magnet. A motor controller is connected to the power source, maybe like a battery pack or some sort of power supply. And the control circuitivity of the form of the analog or the digital input signals. Certifying motor controllers is a relatively newer concept in the functional safety world. Most end users were building their CFSs, so they did not need to include the motor controllers, but now they're realizing that the motor controllers and the starters do need to be included in the CFSs as well. They need to be included in the SIL calculations. The first one that exida certified was the E300, and that was a microprocessor-based electric overload relay that had sensing, control, and communications. The next type of device we're going to look at is an actuator. And if you once again think of it in the simplest terms possible, an actuator is a mover, and an actuator is a component or a device in your CIF that is responsible for moving and controlling your main or end piece of your final element, usually being a valve. There are many different types of actuators. I've listed 5 of the more common types. You have your diaphragm, your piston, rack and pinion, your Scotch yoke, or your motor-driven actuators. And there's always going to be subclasses of these actuators, such as spring return or dual acting. But they will be classified on their main action, such as your rack and pinion will have more gears, more teeth, where your Scotch yoke is going to be that same linear to rotary action, but by means of a lever arrangement instead. One thing to take into consideration when you are considering your actuator, you need to also consider your power source. Is it electric? Is it air? What if that power support source is lost? Can your valve still close or open if it needs to? Do you need to have a backup power source? The final category of final elements that we're going to discuss today are valves. And once again, just like actuators, there's many different types of valves. I listed a couple of the more common. You might have heard of a ball valve or a gate valve, a plug or a butterfly or a globe, but there's many different types of valves out there. Valves, just like the actuators, can be broken down, but are named after the main portion of their body which they're controlling, such as the actuator or the slab or the gate. For instance, you have a ball valve which has your ball actuator in the middle, whereas your globe valve actually has a plug or a stem that closes against the flow. Both of these can be used in safety systems. Both of these can be used in the same applications. However, globe valves are better for regulating flow, whereas ball valves would be better for an on-off control without the pressure drop. When you look at a valve, there are a couple main portions that are going to be the same no matter what, or similar no matter what valve you look at. At the top, you're going to either have a hand wheel or an actuator connected to the stem. Below the stem, or around the stem, I should say, will be your packing, holding that stem in tightly into place. Then you have your bonnet, which is going to protect the stem and also hold the valve body together. Then you have the main valve body itself. This is going to be, it can be one piece, it can be multiple pieces. The valve bodies can be very large, they can be very small, but it's going to encompass the main portion, whether that's the ball, the slab, the plug, the actuator, whatever that is going to stop the process flow. And then around the ball or the plug or the slab, you're going to have some sort of ring or seal or seat. This could be an O-ring, this could be a trunnion, however it is sealed, but you're going to want to make sure when the process flow is stopped, it's going to have a seal around it. When talking about final elements, after you discuss what they are, the next thing that usually comes up are the issues that are associated with final elements. And why is that? Well, when you talk about your SIF, you have your sensor, your logic solver, and your final element. We did a study of over 80,000 SIF designs, and it showed that the final elements contributed about 70% of the demand, the PFD average. They took up most of the PFD average of the SIF. What is the PFD average? Well, that is the probability of a failure if there is a demand on your safety system at that time. So as you can see, 70%, that's a large portion. So it is very important that you choose your right pieces of equipment for final elements, that you're doing the right calculations, and you know what you're getting yourself into when it comes to final elements. So how do you choose your final elements? Well, I like to say, well, start off with your application requirements. That's going to be anything that makes your SIF perform its job correctly. Do you have process flow going through a valve? Maybe that valve needs to close if there is a demand on the system. If that's the case, you will need a close-on trip capable valve and actuator. What if you have a sprinkler system and the sprinkler system turns on by opening up a valve and releasing the water? Well, then you might need an open-on trip application valve and actuator. Well, that's great. It opens, it closes. Does it need to do so quickly? How quickly does it need to be done? What about leaking? If you close, can anything get through? Is it okay if a little gets through? Or is this extremely toxic material that you don't want getting through? You might then need to look at a tight shutoff application. Next, let's talk about what's going through your SIF. What is your process? Is it water? Is it nice, clean, sparkly water that's nice to your equipment and treats it correctly? Or is it a toxic sludge chemical that's corroding your metal and has rocks and other abrasive material that can damage your device? Okay, that was just application. Now let's get to environment. Where's your SIF located? Are you inside a plant that has air conditioning and heat? Is there no fluctuation? Or are you a mile below the surface of the ocean in the North Sea? What about temperature going through of the process fluid? What about temperature of the devices? Once again, are they flexing? Is it very hot or very cold? The pressure. What about force? Torque force and application force. Are you going to put a little extra force in to overcome if you are a static application and any corrosion that might be applicable? What about certified? Do you need a SIL rated product? Do you need to say, well, I'm a SIL 2 SIF? Well, then you might need some certified products. And then finally, what are the cost of these products that we're talking about? So as you can see, it's not just one of these things to talk about, to choose. You need to do a careful evaluation of all. One of those items that we talked about was certified devices. One of the items that can really help drive the success of your SIF and drive your device selection is product safety integrity. As with all products used in safety applications, safety integrity evaluation and justification can be accomplished, and you can do that one of two ways. You can either buy certified products that are already third-party certified and just use them in your system, or you can do prior use justification and do the documentation and justification yourself. It's a process, but can be done. On the back of the certificates that we just talked about is a very important piece of information. And that piece of information are failure rates. Those failure rates predict the probability of failure if there is a demand on the safety system. And that probabilistic performance analysis is a fundamental concept that allows designs to match risk. It allows designs to really be optimized. You can look at cost versus operating costs, and it allows designs to maximize safety without serious weak links. Well, that's great and all, but where does this information come from? Well, there's all sorts of jokes out there that no one knows where this information comes from, or like this comic, or jokes that reliability engineers are just a bunch of academics or theoretical people, not real world people. And, they kind of have a point. When somebody's given certificates for solenoid, that's the same type of solenoid, and one says 400 and the other one says 0.0, it doesn't make sense. So we get asked that all the time. Why? Why is that? Well, it's because there's two main different fundamental techniques for getting failure rate data: estimation technique and prediction technique. And we're going to take a look at a little briefly about each of these techniques of failure rate data. So in predicting failure rates, there are two types of ways. You have your B10 data point and your FMEDA. Your B10 data is also known as cycle testing. You might be familiar with this if you're in machinery applications or constant dynamic operation. An FMEDA is a predictive analysis done that looks at component database and strength and weakness analysis. And that's for low demand or static applications. So the B10 data or cycle test failure data is a technique that really is used to determine the end of life for mechanical or electromechanical devices. It is a method for predicting failure rates, and like I said, if you're familiar with machinery or ISO 13849, you might be familiar with this. The main point of cycle testing or B10 data is it is assumed that all failures are due to premature wear out and that no other failures exist. So it only means wear out. There is no corrosion. There's no leaking. There's no stiction. There's no cold welding. All of these things that can happen. Okay. So if you're going to do a cycle test, you're going to do it on a set of products to make sense statistically. That set of products has to be greater than 20. And you run your test until 10% of the units under testing have failed. The number of cycles is then called your B10 point. The B10 number of cycles is then converted to a time period by knowing the cycles per hour in any particular application. But scaling should be limited to no more than 1 cycle per 10 hours. When you are figuring out your failure rate for cycle testing, you calculate it by dividing 10% of the failure count by the time period. Again, there's an assumption made, but this time it's assuming that out of the failures, 50% are going to be safe failures and 50% are going to be dangerous. So that's something to be concerned about. I know in the real life experience that it doesn't end up 50-50 safe and dangerous failures. Anyway, once again, if you are using this information, please be a couple red flags going out if you are in low demand mode of operation or static mode, because it's only premature wear out It means nothing else could go wrong in your plant. We've done a bunch of research and we've shown that there's other failure modes that really become significant when a product does not move frequently. And sometimes that static or motionless is starting in just 10 hours. Things like O-rings and other seals start breaking down the lubrication in just a week. So your failure modes, including stiction, cold welding, corrosion, binding, all of that is not going to be accounted in cycle testing or B10 data. The other predictive analysis technique is the FMEDA, or failure mode effect and diagnostic analysis. I might slip up and call it FMEDA. But FMEDA is a detailed analysis of every failure mode of every component of a given design. So this is going to be particular for the manufacturer, the model, the mode, everything. If it's a close-on-trip application or an open-on-trip application, if it is cabinet mounted or subsea, or if it has clean fluid or toxic fluid going through, all of that is taken into consideration in an FMEDA. One red flag with an FMEDA is the FMEDA database itself. When you have a database that is going to be kind of shaping your results, you want to make sure that it is calibrated, that it has been validated, that it is up to date, the most current, and apples to apples comparison. What I'm talking about, if you are a subsea application, do not use a FMEDA database for cabinet mounted device and vice versa. So when you are getting an FMEDA done, make sure you know where the database comes from, where those numbers came from is very important. The other way of getting data is estimation. Estimation kind of is happening after the fact. You're estimating failure rates based on failure data already out there. There's three main ways to estimating failure rate data. You have manufacturer field return data studies, you have industry databases, and end user field failure data studies. Just like the B10 and the FMEDA, these estimation techniques have positives and negatives. Once again, always make sure you are comparing apples to apples applications and environments, no matter what source of failure rate data you are getting. We took a look at failure rates just for solenoids. This is just an example. We have this for valves, actuators, multiple different types of valves and actuators. This is just our solenoid, but we wanted to look what the different estimation and predicting techniques compared to each other looked like. And as you can see, the estimation and prediction techniques all kind of came around the same area. However, all but the B10 or the cycle test data point. And this is where that confusion of data or confusion of data failure rates come into play. When people ask me, how do I know what data to trust? I say, well, go to this website. It helps you out so much, sillsafedata.com. You can look up your generic type of device, say a motor-driven actuator or a triple offset butterfly valve, and you can find a sanity check, I call it. It's a low bounds and an upper bounds of where you should see failure rates. Most of the time it's a pretty large bounds, but that can be expected. There can be a lot of different levels of complexity in different designs. But this will at least let you know if your numbers are about right or not. And just to put the graph on from before with the SIL-safe data limit for this type of device, as you can see, that B10, those cycle test data points, once again, below that SIL-safe data. That's when I would go back to wherever I got this data source and question it. But what's the big use? What's the big deal? Who cares if we use correct failure rates or not? Well, let's say, okay, your data is just a little optimistic. What harm can that do, right? Well, let's put in, this is one of our tools, this is Excellentia. Let's put in some optimistic data on just your final elements. We're going to use sensor, logic solver, final element. We're just going to do a solenoid, a valve, and an actuator. Very simple. In this SIF, as you can see, the pie chart is red. It's saying that it's mostly for the PFD average, it's mostly sensors. That's funny. I thought I just learned that it's usually mostly final elements. Okay, well, let's just keep going. Ignore that for right now. Let's see. Oh, our safety integrity level, it achieves a SIL 2. Great, that's amazing. That's what I wanted. It says no redundancy, no diagnostics needed. This is great. I'm set, right? Well, let's look at our final elements. For our solenoid, a valve, and an actuator put together, you have 12 fits. That's a failure unit, a failure in time. And that's saying your mean time to failure is 9,458 years. Well, we know with useful life, you're going to pull that way before then, but what does that really mean? Let's put that in the number of valves. Let's say you have a ginormous plant, and in your plant, you have 458 SIFs. And in that, you're only going to have one valve or one demand on your system a year, one occurrence a year with 9,500 SIFs. Is that realistic? So I kept the sensors the same, kept the logic solver the same. All I did was change out the final element to a more realistic number. This is numbers actually on a SIF that I've looked at. So what does it now? Our pie graph is now blue. It's saying the main contributor to our PFD average is a final elements. That makes a lot more sense. Instead of being 9,500 years, you're at 87 years. What does that mean? If you have a plant with 87 SIFs, you're going to have one demand or failure a year. That seems much more realistic. Instead of 12 fits, you're at 1,300 fits. But remember, that's for your solenoid, your actuator, and your valve, not just one piece of equipment. The bad news is you are now achieving a SIL 1, and barely a SIL 1 at that. However, there's things that you can do to improve the reliability. You can implement diagnostics. You can change your architecture. Maybe you be a 1 out of 2 system. So you can still be that SIL 2 if you need to be. So don't give up hope. But the main point is, even if you just think your data is a little optimistic, it could be unsafe. Well, we're at the end of the webinar. Hopefully you've enjoyed it. We got this information and a lot of this information from a new book out. I'm very proud to talk about this because I'm one of the co-authors on it. It's the newest exida book, Final Elements in Safety Instrumented Systems. If you want to check it out and get more information, go on to our website. You can kind of flip through it. It's divided into 4 main sections. It talks about functional safety and final elements, equipment used, the compliant system design for IEC 61511, and the compliant product development in IEC 61508. So now I'm going to go ahead and take some questions. If you have any questions later on and think of them, please feel free to email me. We're really busy right now, but I'll get to them as soon as I can, I promise. And if you love this and want a ton of more information, we have some great training. We have some great instructors. So check us out. We have some online, we have some in person, and if you want more, go to our website. We only have one very specific question, so if you feel free to email me. And right now we will thank you very much for attending and have a good day.